Thank you very much. It's my pleasure to be here today. I'll be talking about hormesis, its scientific foundations, and biochemical regulatory applications. In terms of hormesis now, what we've come to learn is that low doses of many different types of stressors, things such as exercising, intermittent fasting, hypoxia, heat, cold, ionizing radiation, non-ionizing radiation, electricity, toxins, chemicals, drugs, all of them can stimulate a wide range of adaptive responses. These induced adaptive responses by those plethora of agents that I just mentioned, they have the potential to profoundly affect the success of medical interventions for numerous disorders, things like heart attack, stroke, shock, brain traumatic damage, organ transplant, surgeries. Stresses that trigger adaptive responses also offer ways to enhance healthy aging, improve human performance, prevent damage to tissues, later exposed to injurious levels of various types of stressors. So, in my opinion now, at the center of this adaptive response concept is the phenomenon of hormesis. Hormesis is a biphasic dose-response relationship. It mediates processes by which human adaptation and performance may be improved, optimizing the dosimetry while providing the underlying molecular mechanism. So what is hormesis? How can it be used to achieve these public health and medical advances? Well, I'll give you a definition now. Hormesis is really a dose-response phenomenon, and it's characterized by a low-dose stimulation and a high-dose inhibition. It's a non-monotonic, biphasic dose response, but it's not just a typical biphasic dose response. It has specific dose response features which we'll take a look at. Now, hormesis is kind of the new kid on the block, even though it has a long history. And by new kid on the block means that it's forcing itself to the table, to the dose response table. The two dose responses that I kind of grew up with teaching, writing about, were the other two kids in that slide over there. The threshold dose response model, which is this line over here, and you see if we reach a threshold and zing, we go up, and that's a threshold dose response. And the other player is the linear dose response. The threshold dose response is typically used by regulatory agencies such as the FDA, such as EPA, in their regulation of non-carcinogenic effects. However, both of these agencies and others use the linear dose response when they are dealing with carcinogenic effects, whether they are ionizing radiation or whether it's chemical carcinogens. Typically, the linear dose response is used. The linear dose response has very different implications than the threshold. You can see with the threshold that there is a dose below that threshold which does not differ in response from the control group, meaning it's without detectable biological effect. It means that its exposure is safe below the threshold in theory. However, if you take a look at the linear dose response, the response is really directly proportionate to dose, all the way down to zero. It really means, in an absolute extremist sort of sense, that a single molecule brings with it a theoretical risk, even if you can't quantify this with your instrumentation. In a radiation sense, a single ionization would do the same. Now, so basically, this is the reality that we are dealing with within a regulatory sense. And if you take a look now at the new kid on the block, the hormetic model is really similar to those two at high doses. But it has profound differences in the low dose zone. You can see this little dip below this J-shaped dose response is actually showing a risk that is below the control group, actually a protective or beneficial effect. It's saying that when you reach a low dose zone, things that are typically viewed as being harmful, dangerous, whatever, regulated as such by the regulatory agencies, is actually showing the potential here in this model to actually have a beneficial effect. And that when we have regulations which are pushed down into this level, I will contend here that, and in my writings, that in fact it has a net negative in terms of its public health implications. You have a question?
Is the dotted line a typical response of the control group? Is that what?
Yeah, this is a normalized control group. So it's like at the 100% value. And that's a very helpful question because you'll see subsequent slides that will be normalized to that 100% control value. So thank you very much. Okay. Now, in general, we find when you're taking a look at hormetic dose responses, that they have generally similar quantitative features with respect to the amplitude and the range of response. Now, this was actually very surprising to me. When I first got revved up on this, probably 30 years ago, I really didn't think that this was true. Not that I actually even thought deep enough to even pose the question whether it was true or not. I thought that we were dealing with a low-dose stimulation and a high-dose inhibition, but I thought that this low-dose stimulatory effect, or this J-shaped, we'll talk about why we plot things with an inverted U or a J-shape in a second, but I thought that, gee, you'd have really great evidence for hormesis if you had a low-dose stimulation that could go up by 3 or 4 or 5 or 6-fold, and then at high doses it would decrease. But I realized that you could get a range of, at least I thought, a range of potential stimulations, quantitatively differing. However, I've actually collected, I'm going to say 45 to 65,000 examples of hormetic dose responses in the literature over these years. I have about 5 or so databases created for different reasons to answer different questions. And to my surprise, after looking at probably 4,000 or 5,000 of these, I found that the low-dose stimulation is actually, for the most part, very modest. It doesn't go up by 3 or 4 or 5-fold. It goes up by, in the percentage range, it goes up by usually not more than twice the control group, and usually not more than 30 to 60% of the control group. And this is really made me change my thinking about what hormesis is, what about its implications are, but it also made it, as I think you'll see later on, something that was made things much more understandable for me. Because and it'll lead to the second comment here, because actually way back when I was young, I was an undergraduate, kind of a junior in college in 1966. And I was taking a plant physiology course. And one of our many experiments that we had to do was to study something that caused the dose-response relationship. So the professor gave us this synthetic plant growth inhibitor, and we treated his favorite plant, which was peppermint. And we were to show a dose-dependent decrease in the peppermint growth over time. And so we were doing so many experiments, I'd have to say I had no focus on this peppermint experiment at the time. And then in November of '66, towards the middle of this fall semester, he comes in one day and he says, the group that's doing this dose-response relationship, something unusual has happened. Your plants are being stimulated. And he said, I don't know why they're being stimulated. We do this exercise every semester. He said, it really isn't research. It's to teach you a concept of dose-response relationship. And he said, and the plants are being stimulated. They're not supposed to be stimulated. So if anybody's interested in trying to figure out why something aberrantly is going on, come back and see me at the end of the semester. Of course, the story is that the only one who was interested in going back and seeing this guy happened to be me. And so, so I go back and see him, and my notebook, which I still retain today, is like the end of January of now 1967. And we go back, and we say, well, okay, let's do it all over again. He said, except this time I'm going to look over your shoulder and see what you did, pull out your notebook, try to figure it out, and we'll do it. So actually, make up your stock solutions new, and I'll see if you make them up correctly and how you did it. And so as it turns out, it appeared as though when we made our stock solutions that we had a tenfold dilutional error in the experiment that we did. And so, which is an insight. And so we did it the way he said we should do it, and we did it the way my little research group did it. We ended up having a wide range of concentrations. And this time, with him more or less looking over my shoulder, kind of doing it the right way, at high doses, we actually saw this dose-dependent decrease like he had seen every year. Except our low-dose stimulation, which was that tenfold dilutional thing, still showed a low-dose stimulation. And so that was my first introduction to things biological that could have a biphasic dose response. And so after the little experiment was over, I said, I guess we've answered the question. He says, no, you haven't answered the question. You've just done this now twice. But now you did it better than the first time. You have to do it over again. And because that's what scientists do. They have to verify what they have observed. So I went back and I did it over again, and then I did it over again and came in and showed him my findings. It was still the same biphasic dose response. He said, this is only increasing by about 30 to 60% or so. He said, statistically, he said, this is very tenuous. He said, it may be real, but it's very tenuous. He says, you think you're going to challenge my reputation by getting something like this out in the literature? He says, you have to actually have more proof than what you have. So I said, okay, I'll do it again. And I did this thing 8 times. I said, I'm done. I don't care what happens. I'm done. I'm convinced that I know this is stimulated at low dose. He says, okay. He says, at that point, we had tested around 16 or 1,700 different peppermint plants and all these different things. He said, but we haven't understood why this actually occurs. And so I said, oh. So he says, I think it may be occurring because there's some microbial action in the soil that's changing this compound to something else, and maybe that's why. So he said, let's do this same experiment in hydroponics where the soil is eliminated. I said, well, that's a good idea. And so then I went back and tried to do this thing in hydroponics and set up all the doses, and we had lots of doses then. We were actually running around 12 concentrations and a wide range of things. It was not like 2 or 3 doses, it was a lot. And actually following them over time, we got this low dose stimulation, again, high dose inhibition. This time we only actually verified it about 4 or 5 times. And thank goodness I was done with them. But it took a long time, but it was very useful to me. And I said, I'm never going to work in plants anymore. I decided to become an insecticide toxicologist. I said, this guy is driving me crazy. He's never satisfied, never, ever satisfied. And I came to, well, in the beginning, I just couldn't stand working with him. And I'm glad I went to another area. And I came to appreciate him, as they say, as you might appreciate your parents, forcing you to do something so many years later. I came to appreciate this guy's insistence on replication years later when I got reintroduced to the term hormesis and a modest increase in the percentage zone and a need to replicate and replicate and replicate your findings so that you can demonstrate that it's not a function of background variability or some other kind of something that's unusual in the experimental situation. So, but the interesting thing is that this low dose stimulation can occur either as a result of a compensatory process following an initial disruption in homeostasis, or it could occur with a direct stimulation. Now, we published our work. I never knew the term hormesis. I just said we have a low-dose stimulation and a high-dose inhibition. Published it in the journal, a British journal called Physiologic Plantarum, and I was out of there more or less going into my Ph.D. work. And so, but the interesting thing is that years later I came back when I got reintroduced to the hormesis concept. this fellow from England said that you need to have an initial decrease of some toxicity, and then you'd have an overcompensation response. And he had showed this low-dose dip and then this overcompensation response, and it only would go up by this 30 to 60% range. And so I went back, carried all my data, had my data longer than I've been married. I've been married for 42 years. And still have the notebooks. And I went back, and because we measured things week 1, 2, 3, 4, 5, 6, and so forth. And I went back, and true as it was, the guy was right. Our first week was a dose-dependent decrease. And if we had stopped our research after 1 week, I never would have discovered this hormesis phenomenon for myself. But when I followed it over week 2, 3, 4, and 5, I saw this compensatory growth, and it came out looking like a biphasic dose-response relationship. And I said, this is now looking back over things. Then I began to get an insight as to why the hormetic response was always modest. Because if you were trying to compensate for damage, you wouldn't grossly overstate or grossly overcompensate. You would compensate to try to get back to your original dynamic set point as efficiently and as quickly as possible. And you might it's like, I arrived for this presentation yesterday at about 2:30 in the afternoon. I didn't arrive a week before. It's like you act very efficiently because things cost, time-wise, money-wise, resource-wise, otherwise. Biologically, we do the same thing. If you want to get back to the original set point, you don't want to miss it. You want to slightly overstate it. And slightly overstating means that in the maximum 30 to 60% range. You wouldn't want to, overstate it by 4 and 5-fold. And began to see why the hormetic response was modest. And then it was also interesting to me, I began to see examples where there wasn't an initial toxicity, but where there could be a direct stimulation. And then when I looked at the dose response, and I knew they had to be acting through different mechanisms, I said, when you get a direct stimulation, or if you get an overcompensation stimulation, it's very strange to me that the quantitative features of their dose responses were still the same. And I said, well, how could that be the case? And so then my insight or my hypothesis was actually what the hormetic response was really demonstrating was how much gain there is in the biological system. And it was actually a measure of biological plasticity. And whether you got there through a direct stimulation or you got there through a overcompensation response, you were still capped by this phenomenon. And so to me, it's beginning to make some biological sense. Now, in the world of hormesis, I never really talk about benefit. I usually talk about this as a biological phenomenon. Whether it's benefit or harmful is important, but it shouldn't be part of the definition of hormesis. Hormesis is really a scientific assessment. Because sometimes you'll find that low-dose stimulation is actually harmful. Sometimes you'll find that it's going to be very beneficial. I can tell you that from the harmful side, I've done a lot of work with anti-tumor drugs on tumor cell lines. And most anti-tumor drugs, they kill tumor cells at high doses, but in our experience, and this is a pretty broad experience, shows that most anti-tumor drugs actually stimulate the proliferation of tumor drugs at low doses. And so it's inducing an adaptive response in the tumor cells. And they conformed identically to the hormetic dose response. Even if you take a look at penicillin and streptomycin, and you look at them with harmful bacteria, at low doses, they actually increase the proliferation of the bacteria that they kill at high doses. It's a very hormetic dose-response relationship. So it may be good for the bacteria, good for the tumor cell, but it'd be bad for the patient. So you have to see it within a biological context. Okay, this is kind of the example I was just talking about here. We're looking at chemotherapy, and you can have a typical hormetic dose response with a normalized control over here. At high doses, it does its thing, but at low doses, you get the hormetic stimulation. You can take a look now at a lot of memory drugs. Memory drugs actually have been studied very widely, dozens and dozens and dozens of these drugs in hope for the magic pill. And a lot of them work, and when they work, they show an inverted U-shaped dose response. They actually can increase memory. And at high doses, they actually can decrease memory performance in these animal models. Interestingly, as you may not even think about this, the rise in the increase in memory is really the same increase that you would see in how large the proliferation is of the tumor cells. Why would they increase to the same degree? And you can look at this in a whole plethora of other endpoints. And this is, to me, why I have developed this biological plasticity theory to try to figure out why the increase is limited in very good studies to this 30 to 60%. Now, I study hormesis today for a number of years in a lot of different ways. Experimentally, studying dose-response patterns, statistical significance, the replication, a lot of work on mechanism today, a lot of work on simulation studies when you're dealing with large populations, all in a sense to try to figure out what is going on at this cellular level. Based upon my work over the last 25, 30 years on this with multiple databases, lots of experimental stuff, basically we find that hormesis it's very general. It's a very general phenomenon. It occurs independent of biological model. We see it in plants, we see it in microbes, we see it in invertebrates, vertebrates, humans. We see it in vitro, in vivo. We see it for essentially independent of endpoint. We see it independent of inducing agent, chemical class. We see it at different levels of biological organization, which I find really interesting. So we see it at the cell level, we see it at the organ level, we see it at the individual level. We see it every place. I believe it's a very general phenomenon, a very basic component to life. As I mentioned before, the dose response is typically modest. It's usually in the 30 to 60% range. The width can vary. The width is typically, essentially 75% of our examples in our database are within 20-fold of the threshold, that tipping point, that crossing point, that zero equivalent point. Some 2 to 5% are very, very broad, very wide. And why are some very wide? Why are some much more narrow? And I don't know the answer to that question. I think it could have to do with the degree of homogeneity or heterogeneity in the cells of the population that you study, but that's an area to be studied. This is the typical example of a hormetic dose response. You have the normalized control group, you have the little low dose stimulation, high dose inhibition, you have the little threshold here, and toxicity or inhibition at the high dose. Most people would say, okay, you have toxicity, it kind of goes back to the control, and you should have experimental bounce or noise here. But we got to flip over to the other side. And that's where the hormetic thing is. A lot of people in the good old days would say that's, you're just deluding yourself, Calabrese. That's just experimental error. You want to believe something that doesn't exist. And I've spent actually quite a bit of time convincing myself that I'm right and they're wrong. And then after that, I have to now play by the rules of the game and their criteria are the criteria set up by the field to establish that such phenomenon is real and not variable. And you can begin to see why the wisdom of my old advisor, you have to replicate this thing, you need lots of doses, and you have to replicate it, and show this. And with good statistical activity, in today's world, you have to be able to find mechanisms that essentially can explain and the mechanisms that mediate this stimulation and inhibition. And in the last 10 years, those mechanisms have come to be. And last year, 2 years ago, we published actually specific hormetic mechanisms for 400 different dose responses with mechanisms down to the receptor and cell signaling pathway, which were very definitive for each of those 400. I have another 600 that I have that will be sent out fairly soon. Hormesis could occur for everybody, whether you're normal or whether you're a high-risk group, except if you're a high-risk group, it's kind of shifted on the dose to a lower dose, but basically the quantitative features of the dose response for hormesis are the same. I was actually criticized, this has almost never happened probably to anybody, but I wrote a paper for an annual review of public health on hormesis a number of years ago. And so usually when somebody writes an annual review, you're supposed to be thought of as knowing something about the topic. So I wrote this paper, it came out, and one of the editorial board members decided to challenge me by saying that you never addressed the concept of high-risk groups, and he wrote a separate paper in the same issue of the annual review saying what the limitations of my paper were. And I actually have never seen that done before in an annual review. But I tried to take it as a positive, and but it was a good question, and I hadn't addressed that question. So I went back into our database and found that there was a lot of information on differential susceptibility, and we then published a subsequent paper 2 years later addressing his point and showing essentially the little schematic that I showed you there. So criticism can be good if you listen to it, and objective criticism. I want to share with you that in the beginning of my stay with all this, I have to tell you, when I was beginning to make my move on Hormesis, getting a lot of funding mid-90s, later 90s, I'm a toxicologist, and I try to publish my papers in our society's journals. And I had 6 papers on toxicology, on Hormesis, that I thought were pretty substantial. I sent them to my journal, which was Tox Sciences, and I got kind of good reviews on 6, and I got rejection, 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 rejection. And you know, at my stage at that point, I mean, yeah, I keep getting rejections even today, but you know, I kind of can sense based on the reviews what the editor should say. You know, accepted with minor revision, major revision, this and that. I was just getting, with pretty, not bad reviews, clobbered with the final decision. So I call up my grant manager, and I say, I think I'm doing really well on this, but I'm getting rejected by this top journal. And he says, Ed, he says, if you want your grant renewed, you have to find a way to get into those journals, or it's not going to get renewed. So at that stage, I could have just kind of blown it off, because I really didn't need his grant money anyways. So I said, what am I going to do here? I mean, because, I mean, the sign of idiocy is, right, doing the same thing over and over and over again, I guess, and getting the same result all the time. I mean, 6 times in a row, I still hadn't learned my lesson. So what I did was I said, all right. I said, I'm going to invite these guys, this editor-in-chief who thinks he knows it all. I'm going to invite 5 people who made their name on low-dose linearity, and I'm going to invite them to a big debate at my university, invite the world, so to speak, to it, and I'm going to pull a Fidel Castro, and I'm going to talk for 6 to 8 hours on Hormesis on day 1. I'll allow them to talk as much as they want and criticize me on day 2, and we'll see who's left standing on day 3. And so that's what happened in the year 2000. I did that. 200 people showed up. We advertised it widely. My grant manager's there. I did my 8 hours on Hormesis. Everything I knew. You guys won't have to, you know, put up with that, really. But as it turns out, I came home. My wife said, "How'd you do?" And I said, "I was just awesome today. The best 6-hour talk I'll ever give on Hormesis, right? The only one." I said, I think I convinced the world. I think I convinced them all that why I'm right. So I showed up the next day, and the first talk was by this leading biostatistician. He says, because I had sent them all 150 articles 9 months before the meeting. I told him, this is what I want you to look at, why I believe what I believe. This guy shows up and says, he sent me 150 articles, seriously. I mean, I'm going to read 150 articles this guy sends me. I'm pretty busy. Skim through it. I'm just going to assume that he's correct. But you know, he said, I looked at his first database that he created, and that database is actually seriously flawed. And I'm saying, uh-oh. And because this is a really smart guy. And he says, you know, he says his database, but he said, I consult a lot for the EPA and FDA, and he said, and they'll say, well, Calabrese published a number of studies on this, and isn't Hormesis real? And he says, well, it's not so much as it's real or not. The issue is it's significant or not. He says his database can show examples of Hormesis because it's based upon essentially evaluative criteria, and it could be rigorous, he said, but Calabrese didn't actually use a priori entry criteria in putting this first database together. And so that's like saying, like a baseball player, did you have a good season last year? And you could say, I got 150 hits. Well, how many times did you get up? well, you could have been up 300 times or 600 times in a season. And it makes a big difference in your batting average. Calabrese, what is hormesis? Does it occur 100% of the time, 50% of the time, or 2% of the time? His database can't answer that question. And I said, oh, crap, he's right. And so I said, my grant manager's there, and I'm seeing him writing down things on his paper. And then the next guy got up, so it was a hit, I think, I took pretty much in the stomach and nose. And then the next guy got up, who was from Tox Sciences, the editor-in-chief. He says, I don't even care about this debate over frequency of hormesis. He says, in Tox Sciences and toxicology today, we worship at the altar of mechanism. And until he can explain it, he's not getting in my journal. And then the next guy got up, and the next guy got up, and the next. And at the end, I'm not sure if you've ever seen, Rocky Balboa and Apollo Creed. But I kind of felt like Rocky did after 15 rounds with Apollo Creed. And so I came home after the second day, and I said, well, the second day go better than the first day? And I said, I'm still standing like Rocky was, but I'm a bit groggy, to say the least. And so, nonetheless, I scored my points. Wasn't totally defunct, but I realized that I wasn't quite ready for the prime time. And so I went to work really hard, created a database with the help of this biostatistician that had good a priori entry and evaluative criteria, looked through 21,000 papers, this and so forth and so on, ultimately came up with an answer to the frequency question. And ultimately, it was approximately 40% with very rigorous a priori entry and evaluative criteria. Sent the paper to Science, and they didn't want to look at it. Sent it to Nature, and didn't want to look at it. But we actually got it in Tox Sciences, and it was highlighted and profiled, and was given a strong status there. And so as it turns out, this was a big breakthrough because Nature picked up on it. And then they invited me to write a special article later on that made it into their press package. And the next thing I knew that there were front page stories in a number of newspapers, and got my picture in U.S. News and World Report, Wall Street Journal, a whole bunches of things, and became famous overnight, so to speak, on the hormesis front. I also developed a lot of enemies on the local front because I was proclaiming that it had strong regulatory implications that could replace some of the other models. And so it kind of cut both ways. Now, it's kind of a little history to it all, but I want to say that over the course of time now, as I mentioned before, with new technologies, developed really good mechanistic insights. And we found that the hormetic dose response is also independent of mechanism. And that, you might find that odd, that you can induce this by a plethora of different mechanisms, and it doesn't make any difference what the mechanism is, you still have the same quantitative features of that dose response. Very, very interesting situation. It's consistent with my plasticity hypothesis, actually. So now I have several hundred, I have close to 1,000 examples today that are pretty good. So now the next slide here shows you kind of an example of a hormetic dose response with sodium arsenite, and it's looking at the human embryo lung fibroblast cells that were published by a group in this country. And they showed a low dose stimulation and a high dose inhibition. Then they took some receptor cell signaling pathway inhibitors, and they could actually block this increase by blocking the pathway. So it told us that these pathways were instrumental to explaining the stimulation. We also found that those pathways which mediated this particular stimulation, they basically had no impact at high dose. But there was a different mechanism that could block that inhibition at high dose. So it showed that in this particular case, we could begin to identify two mechanisms that could begin to explain the stimulation and the inhibition. It's really getting to the point where that editor really wanted to see this. Now, and I have, as I said, probably close to 1,000 examples of those kinds of things. I'll show you a few more later on. But the hormetic responses themselves deal with integrated responses across multiple biological levels of organization. You see hormesis for cell proliferation, for fecundity, tissue repair, learning and other behavioral endpoints, diseases, resistance, DNA damage, tumor incidence, aging and longevity. Anything that's important to you, you'll find hormesis relating to that endpoint, essentially. I'll give you some examples here. These are just chosen to show you the diversity, really, of hormetic dose responses. This is the effects of ethanol, acute ethanol, on social behavior in adolescent rats at day 30. You can see, not unexpectedly, that high doses really just silences their social behavior. But at low doses, it actually activates them considerably. But they're in this 30 to 60% range. It's a very reproducible assay, by the way. This is a fruit fly study with methanol, very toxic at high doses, as you can see, but at low doses, this toxic agent actually extends the longevity of male and female animals, fruit flies. This over here is arsenate. At high doses, it inhibits the stimulation of the lymphocytes in this assay. You might expect this should just be random bounce at the bottom, but it flips over. These little dots at the top indicate statistical significance. Here we have the most toxic element that EPA is concerned with, really. PM10, I'm sure that I mean, any dose just kills you, as we heard what Lisa Jackson said. But basically, methylmercury is really considered to be, I think, their most feared pollutant. It's a potent neurotoxin. And this is a neurotoxic assay, actually, and at high doses, it actually destroys these neuronal cells. But look at this, at low doses, it actually enhances the viability of those cells. It's a very, very interesting phenomenon. This over here is more of a biomedical one, and actually I was doing a review of a lot of work in the neuroscience area, and this is studies in the seizure area. And seizures are studied by inducing seizures in animals by different ways, and this is what biochemical called PTZ induces seizures. And in this particular study, they then treated the animals with morphine. And once you treated them with morphine in this zone, it took more PTZ to induce the seizures. This identified morphine as a potential anti-seizure agent. I looked at this and I said, hormesis. It follows a biphasic dose response. It conforms to the area of, to the magnitude we're talking about. Very large number of doses. Then I went into the seizure preclinical literature. I found about 80 different chemicals tested preclinically for seizures with animal models. And they all showed an inverted U-shaped dose response. I said, this field is just dominated by hormesis, and the seizure experts don't even know it. Then I went into the anxiolytic drug area, the drugs dealing with stress and so forth and anxiety. And you can study this in animals by taking rodents. They don't like to go in open areas. You put them in an open area with a lot of light, and they will not spend their time there because they're at risk. Now, if you can get drugs to make them spend time in the open zone, it's helping them, it's interpreted to overcome their anxiety. It's like getting me to drive into New York City. And you can see here with this drug, DHEA, at low doses, it increases the time that they spend in the lighted zone. But at high doses, it actually makes it worse. So low dose stimulation, high dose inhibition. The anxiolytic drug literature, just like the anti-seizure drug, the preclinical literature is loaded. It's totally dominated by a hormetic dose response. And the pharmacologists for the drug companies don't actually even appreciate that at all. This over here is the resveratrol component of red wine. It's considered perhaps one of the factors why a glass of wine a day is good for you with cardiovascular health. And you can see a biphasic dose response here, looking at myocardial infarct damage and so forth. And you can see at low doses you get a decreased risk, but at high dose actually the risk can go up. Now, I started the presentation talking about preconditioning when you stress an animal. And over here, I'll kind of give you a little preface to this. Back in 1986, investigators at Duke were studying myocardial infarctions and ways you perhaps could modulate these. And they wanted to look at what would happen if you pre-stressed the animal with very slight, but I would say slight to modest hypoxic stress a day or two before you induce the myocardial infarction. And what they found when they did this, they found that the animals that were moderately, lightly stressed with hypoxic stress a day or two before they got the major myocardial infarction, they had about 80% less damage than those that didn't have the pre-stress. It was kind of the equivalent of giving an angina, having angina pain a couple of days before the heart attack. And these investigators were shocked really with the magnitude of their discovery. They replicated their work, others replicated their work. They then extended this to look at other organs, to the brain, to the liver, to the kidney, to skin. And preconditioning became a massively significant finding because there was this upregulation of adaptive mechanisms as a result of being exposed to low-level stress that would then protect against subsequent stress. Then others, as you know, investigators do, they decided to induce the heart attack and give this low level of stress after the heart attack, which I figured could never possibly work, and they got protection, the same degree of protection. And this is actually revolutionizing the field today in terms of trying to find ways of really slowing down various types of diseases, protecting you against all kinds of potential trauma. This over here, of course, it now has a very strong experimental basis. Here you're giving a low dose of carbon, you're giving essentially a low dose of hydrogen peroxide, and then you're giving it a somewhat substantial dose, more massive dose later. And at low doses, you can see these low doses, prior low doses, protect against the initial, the subsequent challenging dose. But at higher doses, the protection goes away. So there's an optimal level, and you can see that this preconditioning dose conforms very nicely to a hormetic dose response. Over here, this is another example of the same, except this is looking at myocardial damage in a Sprague-Dawley rat, and giving the nitrite 15 minutes prior to the cardiac damage causes a nice J-shaped dose response. This little blob over here describes various types of research that was done to identify pathways that mediate this protection, showing a mechanism here. The point of it is that this low dose, this hormetic activity is really explaining this preconditioning phenomenon. Now, on the cancer side of things, environmental side, this is a study that's showing gamma rays and lung adenomas. And it's a big study with each little blob over here, triangle, square, having about 500 to 750 animals. It's a big study. And you can see that this gamma rays are supposed to cause cancer in a linear fashion, but actually they don't. There's a low-dose effect that is decreasing the risk by about, 30 to 40%. Higher doses, it goes up as expected. It's very inconsistent with the linear dose-response relationship. This is a study out of Japan looking at effects on this DD mouse strain, which is predisposed to developing diabetes. Now, the group got this 0.65 milligray per hour. It's equivalent to about 65 times higher than background, and they got this throughout their whole life. And you can see here that the ones in red are the ones that had the radiation, and the unexposed group would be the control, and these really outlived them by about 25 to 30%. Now, in the next slide, it doesn't show it up particularly well here, but I think you can see it here. This is the control group at 90 weeks. It really looked like my dad. My dad lived to be 95, and at 95 he was what you call well-worn. And when I look at this slide, it reminds me of how my dad looked at 95. He was thin, his hair was falling out. His mind was still good, actually, but he was really well-worn, put it that way. The same age, this animal is, the fur is full, it's shiny, it's plump, it looks healthy. I said, give me that. And that's the low-dose radiation group. I said, if that was coming from a drug from Costa Rica, they'd be trying to sell it. But it's low-dose radiation, so it actually is bad for you. So it's a very interesting phenomenon. I've seen this in a series of papers. This is not the only paper, a series of papers by really good investigators in really good journals. And even if people, see, what I don't understand is why these inconsistencies with LNT don't make people who believe in LNT wonder, are they right? If these data are reproducible, which they actually are, what does that mean to your theory, to the universality of your theory? It has to be a problem. Actually, it has to be a problem. This over here is looking at radiation gamma rays on lifespan in crickets. And at high doses, it wipes them out, but at low doses, you get that same degree of stimulation. We're looking at the effects of X-rays, I think we have X-rays, gamma rays on mutations in the fruit fly genome. This is the same model that Hermann Muller used, who got the Nobel Prize for showing that X-rays could cause cancer. Muller looked at the high-dose group. High doses, way out here someplace. If Muller had just lowered the dose, they might have given him 2 Nobel Prizes. Over here, an investigator, Dr. Redpath from University of California at Irvine, I think, he shows the same type of dose response looking at neoplastic transformation frequency with a human non-tumor fibroblast cells, a nice J-shaped dose response. These are kind of representative of different aspects through the cycle, cancer kind of a cycle. Over here, DDT is banned because it causes cancer in the male Fisher 344 rat. And it does. It actually causes cancer at high doses. Japanese investigators have used a predictor of liver cancer, the liver foci. And at high doses, they show that at high doses, you get these transformation changes. The Japanese, however, decided not to look at just 2 or 3 high doses. They decided to look at a lot of doses. And what they found was something weird happened at low doses. They actually got a decrease in the liver cancer cells. And they also then looked at this in tremendous mechanistic detail to try to explain what is going on at high mechanistically and low. It really opens up a whole other way of looking at this. Over here, you may have heard of the Mega Mouse study, 24,000 animals, try to figure out what the nature of the dose response was. The FDA took this chemical, 2-acetylaminofluorine. They tested it as I say, in great detail, and they found, yes, indeed, it was a bladder carcinogen, nice dose-response relationship, but they looked at low doses, and they had 6 major rooms with thousands of animals in these rooms. Each room showed the same J-shaped dose response. The U.S. Society of Toxicology put a great board together of 14 people, and they claimed that this dose response, J-shaped, was real, was hormetic, and was in contrast to the LNT. Now, the hormetic dose response has a lot of applications. Affects drug development for anxiolytic, anti-seizure, memory drugs, osteoporosis, wound healing, and really many more. It's inherent within biological systems. You have this preconditioning and postconditioning also explains the hormetic biphasic, hormetic dose response explains their phenomenon as well with a mechanistic underpinning. So essentially, what happens now when you have multiple memory drugs? If let's say there's an Alzheimer's patient and you can get memory boosted up, and actually I have a friend of mine, a retired UMass professor who was just diagnosed with Alzheimer's. He's being treated with a particular drug. He's getting some little benefit out of it at the present time. His wife is really going, kind of crazy, trying to cope with her situation. And so what happens if they could give, increased his set point up to a certain level, maybe they could give him another drug on top of that. What happens if you layer on 3 or 4 or 5 drugs that it might be effective? And it's a good question. And the data that I have seen when people have actually tried to do that in animal studies, where you have grids of this drug with that drug and multiple drugs, and how you can try to tease it out. And actually what you find is that, in fact, you can't get beyond that 30 to 60% grade. You just can't do it. You can get synergies if you lower the dose low enough and get synergies under that 30 to 60% zone. But in these studies, you can't do it, and I've seen that in a dozen or so to other studies. And so to me, it's telling that you're pushing against this cap. This has huge implications for the pharmaceutical industry and others, because when you are trying to have drugs that deal with seizures or anxiolytics or memory or other things, osteoporosis and the like, all acting biohormetic drugs, you are constrained by the gain in the system. And you're not going to go, I don't think, beyond this 30 to 60%. A lot of people are trying in the world of metabolic engineering. They lay on 500 genes, they do this, they do that. You try to tweak the system. It's very hard to break through redundancies that are trying to, the metabolic redundancies. So what is hormesis actually indicating? Hormesis is really, it's a low-dose stimulation, and it's different from high-dose toxicity. The low-dose stimulation, in my opinion, I believe it's measuring biological performance. It's not really measuring toxicity. It determines how much the system can respond. It's the first quantitative estimate of biological plasticity. The hormesis stimulatory response is constrained by the limits of plasticity. Now, try to put this all together. Hormesis is a general concept, and it's a central biological concept. It affects all disciplines that utilize the dose response, and really everything in biology is going to be using the dose response, concentration response. It represents a general adaptive strategy through which biological performance is enhanced and mediated. It provides both the theoretical basis and the molecular foundations to create biological shields to protect against chemical, radiological, and microbial threats. And I love to ride a bike. I ride many thousands of miles a year. And Sunday after Thanksgiving in 2010, I took off on a 50-mile bike ride. I was coming back home through the UMass campus. I live about a half mile away. I looked at my watch, and it was 6:02, and I said, oh, great, the Patriots are playing. I'll watch the second half of the game, be great. And the next thing I knew, I fell down. And I was lucky, in a sense. I was right next to the Amherst Fire Department, but it wasn't so lucky in that I had broken my pelvis in 2 places. Not a good day. And so they came out, and they dragged me to the hospital, and a couple days later, I saw this big black and blue down my right leg, and I said, what's that? They said, oh, you were just bleeding like crazy, and you're lucky that you weren't out in the farm country someplace, because you just could have bled out and died there. Lucky you fell down next to the fire station. And so then about 3 months later, 4 months later, I'm searching the internet, and I see this study from this guy from Toronto who's looking at shock. And they're removing blood from these animals, and then they are preconditioning them with a remote method, which is taking a blood pressure cuff, pre-treating them on their back leg, and then they are giving them the shock treatment. And they're finding that the preconditioned animals have about 70 to 80% less damage than those that didn't get it. And I'm thinking, wow, maybe I should treat myself, day before every single long bike ride. But the point is that shock, loss of blood, and so forth is really significant, especially for soldiers' wounds and other kinds of things, could be very significant. Also, this preconditioning, remote preconditioning, which people can use with a blood pressure cuff with various methods and so forth, it could be used. This will protect the brain against subsequent damage and other kinds of tissues. Preconditioning is used in a lot of ways to enhance the functioning of stem cells and the like. Very big, very significant. But the issue is improves functioning, creates biological shields, could really help with protecting from harmful aspects with stressful surgeries, lots of different things. This has implications for numerous and diverse medical interventions, as well as affecting health and performance of military personnel, athletes, and the general public. Failure to consider hormesis, and it's been totally failed. I mean, hormesis has just been, I'm calling it the new kid in the block, but it was marginalized, ridiculed, anything you want to call it, throughout the 20th century. And the failure to consider hormesis within a hazard assessment and risk assessment is really a serious failing of modern risk assessment. Risk assessment needs to consider the entire dose-response continuum. Actually, it needs to consider basic biology, understanding, not be victimized by using only high doses and a few high doses and thinking that the biology is the same at low doses. It actually is not. And there's too much data now to suggest otherwise. Hormesis can play a role, significant role, in drug discovery, drug development, and evaluation. And in my opinion, hormesis should become incorporated into educational programs dealing with the dose response. Thank you very much.
Great job, Ed. I think everybody here, of course, is familiar with the climate change debate, and there's an incredible similarity between the hormesis problem and climate change. The science is totally ignored. But I want to ask you, 40 years ago, Walter Hybe wrote a 1,100-page book on hormesis that seemed to have been ignored. Where was hormesis, back then? And this predates your work in it.
Well, hormesis, I think hormesis got its start, its real modern start, put it this way, with the work of two people, one on the radiation side, one on the chemical side. On the radiation side, he spoke in here, he died a few years ago, Dr. Lucky. He made the move back in 1980, published a book, Ionizing Radiation and Hormesis. And Lucky was actually more insightful than anybody, because in 1975, I found in the preface of a book that he published, before EPA began their regulatory practices, really, Lucky said, the hormetic dose response is significant, it's a real component of the dose response, and regulatory agencies would be very wise to consider this as they go forth on their activity. I mean, he was actually prescient, he was ahead of us all, and at the same time, at the very same time, Dr. Anthony Stebbing from the Marine Biological Research Station in Plymouth, UK, was making similar discoveries, looking at metals in the marine environment, and came up with very comparable things. They never really communicated with each other, but they were very independent and very significant. And a third person, Dr. Elmer Zabadi from the University of Liverpool, did the same thing pharmacologically in the late 70s. And so those three, for me, they had persona beyond one paper and book and so forth. And for me, what I have done is basically, they brought it from, they separated hormesis from the historical antipathies and relationships to homeopathy to really central core science. And I viewed those as my role models, but things have then moved on from there. But those to me, but that was circa 1975 to 83. And then what happened to really make it big was the in vitro revolution of the 80s. It allowed us to go in vitro and allowed us to test lots of concentrations at the same time, which you couldn't really do with whole animal studies. And now about 80% of the papers are in vitro. So the in vitro revolution dovetailed with that and my own stuff, I think, to push it ahead.
Hi, I'm Howard Hyde, and I have a doctorate in nothing. My father was a nuclear scientist, and my brother's a physics professor. I remember reading a story a few years ago about a city in Asia, someplace, where it had been discovered that some cluster of buildings had above legal levels of radon or some other radioactive material in the building materials, and this caused a great shock, and they took measures to mitigate this. But in a subsequent follow-up study of the rates of cancer in the area, they found that the cancer rates were actually lower clustered around these buildings that had the radon in them than in the larger area. And I think that somewhat fits the theory that you're talking about.
It does fit, and I actually invited the investigators from directed that study to one of our conferences. Their papers have been published. They're out there in the literature, and it's a significant, unique opportunity to study these types of effects. But yes, it does exist. It's out there, searchable, and should be read.
That particular paper was published in our JPAN's Journal of AAPS. There was apartment buildings in Formosa that were concrete buildings. Cobalt-60 had, I don't say contaminated, I say enhanced the rebar. And you're right about your statements there. Thank you so much, Dr. Calabrese. You showed initially the linear, the linear line, and then the threshold and straight line. I know that these are used extensively in the regulatory sphere. Are there any real-life examples in biology where the linear response is the true response? Every single curve you've shown has been curved one way or the other.
It's a really basic question, is where did the LNT come from? Actually, that's going to be the topic of my next presentation today. And so if it's okay with you, I will answer that in the next presentation, because I will spend quite a bit of time on it. Next question.
Ed, great talk. I really appreciate it. One question I had for you. You said hormesis applies, what was it, 40% of toxic stuff exhibits hormesis?
Actually, what I specifically said was when we went in with extremely rigorous a priori entry and evaluative criteria, our study showed that 40% satisfied those criteria. If we had loosened them up just a little bit, we could have easily bumped that over to 65 to 70%. Okay. And then there are other reasons why you have statistical reasons that just don't show things. I think that hormesis is far more common than the 40%. But I had to be so darn tough on the study so I could make sure that I handled all the criticisms possible, that the criteria that we used were actually unreasonably severe. And understated what the actual occurrence was in that particular study.
So my follow-up is the two big bugaboos that are out there in terms of toxic stuff, lead and asbestos. Is there anything you have in the data or anything you've read that may also apply to those two biggies?
It's interesting. I have looked at both of those, as a matter of fact. I have actually a substantial amount of literature on lead to show hormetic dose responses in multiple biological models. I've actually in the original work that was published by Dr. Needleman, that really turned the field on its head with respect to lead back in the late 1970s. The original papers actually have hormetic dose responses in them that apparently, at least in my opinion, they look pretty strong as hormetic, and were not dwelt upon. But I have lots of other aspects with lead showing hormetic dose responses at low doses. As to the asbestos one, that's more problematic. It hasn't been studied within that fashion, but I do have a series of cell culture studies, a multiple series of studies with cell culture that do show hormetic effects with some asbestos fibers. That actually is an interesting thing to follow up on.
Hey, I'm sorry. In orthopedics, we all have colleagues that have developed lymphatopoietic disease, and we're always exposed to radiation. And I have to say, they tend to be the guys that refuse to wear lead in the OR. But for those of us who actually do wear lead, I mean, I've always wondered, what is the dose response curve? Where is the beneficial radiation dose? You know, we think that that's due to, and there have been a number of studies, it's due to total cumulative lifetime whole body irradiation or radiation dosage. Do we know what the optimal radiation dosage for humans is? To be like the mouse?
Well, it's a great question. I'd have to say that's a great question, and there are a number of ways to try to address it. But I'd have to say that the answer might not be really satisfying, because the optimal dose is really tied into the endpoint that you're looking for. For example, if you're looking for a cancer endpoint, I believe there will be a J-shaped response for a cancer endpoint, but it may depend upon the tumor that you're looking for. If you're looking for radiation to enhance an immune response, which it does at low doses, it depends on the particular immune response. However, I would say that in general, the optimal response is above background. So what we are living in today is a probably suboptimal radiation, ionizing radiation exposure to optimize the activation of, I'm going to say, certain types of immune responses that could be useful and other endpoints. So it's kind of a squishy answer, because I really have to sit down with you and try to figure out which endpoints are important to you and which ones are important to me and which ones are important to others.
Well, I guess I was interested in all-cause mortality, but I mean,
okay.
Mostly, I mean, we just don't want to die in our 50s of, lymphatopoietic cancer, but we're all above baseline. So the issue is how far above baseline we should be and what we need to, because it does impact how much pounds of lead we wear and how much we really, there's a cost, it's just like EPA. There's a cost of doing business, and it's standing for 12 hours and 35 pounds of lead versus 50 pounds of lead,
As you can see in the studies that I gave for the model, the strain that I provide you with there, and I have many others along these lines, that those animals were getting 65 times greater than background for their entire life, and they had beneficial components for them. How it plays out epidemiologically that's another question.